Okay, HL Juniors, another little lesson which is just an extension of area. You may have a couple of questions like this on your exam, so I just wanted to make sure I went over it with you. It's really pretty easy stuff. Okay, so I just wanted to do a quick review on, net and total distance traveled. So remember, we have some line here, y is equal to x. I just kept it simple. And just remember that the net distance traveled is equal to the area from A to B under the curve. So between the curve and the x-axis. Okay, so I'm looking at this stuff here, right? And what net area is going to do, it's going to take the area above and it's going to subtract from it the area below. Now if the area below is a bigger region of area, then your distance is going to take on a negative value, even though the distance itself isn't negative. Okay, so anyway, the net distance, all you have to do is compute the definite integral from A to B of whatever your function is. Okay, so this is simple. These are triangles, and if I compute geometrically this area here from -1 to 0, my area is 1/2, but it's 1/2 below, so you can think of it like this, right? And the area above is 1/2 of 5 times 5, and so the area here is 25 halves. Okay, so the net distance formula says, geometrically what we're going to do is we're going to take the area below, above and subtract from it the area below, and when we do that we get 24 halves or 12. So the net area here is 12. Now if I want the total distance traveled, so the net distance traveled, I kept saying net area, but it is net area, but it represents the net distance traveled. The total distance traveled, well, the difference here is that we're going to take the absolute value of whatever is negatively valued in the function. Okay, so again, it's the area between the curve and the x-axis, but if I use the same example here and I take the absolute value of this function between -1 and 0, it brings that area up. You can do it on your calculator to see it. In fact, I'll do that real quick. Just let me just clear this out. If we go ahead and put in our function and graph it, all right, what I can do is I can compute this thing. I can do math 9, which is the integral from -1 to what did I have, 5, right, of x dx. And if I hit enter, I get an area of 12. Okay, graphically speaking, I can do second calc 7, okay, from -1 to 5, and what that will do, it'll shade in the area and it'll give you the 12 you see there, the net distance traveled of whatever this object is. Okay, now if I take the absolute value of the function, which is math right arrow 1, and I put my x in there and I graph it, what happens is it takes all negatively valued output values for the function and brings them above the x-axis. So that way, if I do second calc 7 again and I go from -1 to 5, I'm going to get the total distance traveled, which is 13. Okay, so I was trying to demonstrate that there, but in this case we're going to sum up the areas, and the areas are all going to be above the x-axis. So anyway, there's my 13 there. Okay, in the net distance traveled case, we're still looking at area between the curve and the x-axis. The difference is we're subtracting the area below from the area above. Okay, and either way you can do that with the definite integral. So if you're asked for total distance traveled, make sure, if you're using your calculator, put the absolute value symbols around your function, and regardless of what, this was positive to begin with, just that little piece was negative, just put the whole thing in absolute values, and as you saw in that last one when I did second calc 7 from A to B, it computed it properly. Now what's going to be new to you is the volumes that are formed by these regions of area. So we're going to start with the disk method. So let's talk about it. So I'm just going to take the same function, y equals to x, right here, from 0 to 5. Okay, so I have this little triangle here. Now if I rotate this thing around the x-axis, I get this sort of cone looking figure here, and it's solid as a rock. Okay, there's no hole in the middle there, it's just a solid cone, like a plastic cone I would use in geometry or something. And the idea is that, you know, you're going to have to tell with a volume, are you going to use a disc or are you going to use a washer method? There's only two for right now anyway. And how you figure it out is that, you know, if it's strictly area between a function and the x-axis, is always going to be disk. In other words, if I slice this thing perpendicular to the x-axis, what I'm going to have are these circular cross-sectional slices. And that's good. We denote that as a of x. That's the circular cross-sectional slice. And we know that since it's a circle, then the area of that circle, so remember, these slices are going to be super thin, so thin that we couldn't compute a volume. It's not true, but you have to think of it that way. So what we want is the area of one of these cross-sectional slices. And the area is just pi r squared for a circle. So the idea is we're going to use this function, pi r squared, where the radius is going to be the distance between the axis of rotation and the curve. So this would be my radius right here, because x-axis is the axis of rotation, and that distance is just the function itself. So since my function is x, my formula that I need to integrate is pi x squared. I'm plugging an x in for the r. Okay, so the radius is just going to be the function itself. And when we integrate area, we get volume, okay, from a to b. So it's really super simple to do. So let's do a couple. So I put some notes here. Okay, the disk method, this is going to occur when you rotate a region of area between the curve and the x-axis. Okay, so it's like solid area between that function and the x-axis. When you slice the figure perpendicularly to the x-axis, you get a circular cross-section. Okay, and I should put here that area function is denoted a of x, and it's pi r squared because that's the area of the cross-sectional face of that circle. So if we want to find the volume, then we just integrate that thing from a to b, whatever values they give you, limits they give you, of area. So the antiderivative of area is going to give you volume. Okay, r is always the distance from the axis of rotation to the curve. Later on, we're going to start, you know, spinning around the y-axis, so things are going to change, but the radius is always the distance from the axis of rotation to the curve, always. Okay, and again, if we integrate this area, we're going to get the volume of the solid. So here's our little function y equals to x, right? And we've got this area here. And if I spin it around the x-axis, I'm going to get this conic looking thing. And again, if I slice perpendicular to the x-axis, I'm going to get these circular solid discs. Okay, so I know the formula I need to use is pi r squared, where my radius is x. Here's the axis of rotation, the x-axis, so the radius goes from the axis of rotation to the curve. That distance is just the function x. It's whatever function they give you. If that were x squared, then the radius would be x squared. If it were x cubed, it would be x cubed, and so forth. Okay, so now that I have a function, a geometric formula, and I plug my function in to get my area function, now I can integrate that and call it volume. So volume, this went from 0 to 5, so the volume is from 0 to 5 of pi x squared dx. Generally speaking, you're going to pull the pi out, okay, and just deal with integrating what's in here. Pretty simple integration. We get x cubed over 3 times the pi, and now we have to use fundamental theorem of calculus to evaluate that. So it's pi times 5 cubed is 125 over 3rd. If I plug a 0 in, I get 0. And so I get 125 pi over 3 cubic units. In the next example, a lot of times you're going to get it in words. You're not going to have a picture, so you're going to want to make a little sketch. Okay, find the volume of the solid obtained by rotating the first quadrant region bounded by y equals to x squared and the lines x equals 1 and x equals 2. Well, here's y equals to x squared. And here's the line x equals to 1 and x equals 2. So this is the area I'm talking about. Okay, and again, you know, if I rotate this thing, it's going to look something like this. And if I slice it perpendicularly, guess what? I'm still going to get circular discs, so I'm still going to use this formula here. Okay, the thing is that, you know, I need to orient myself. What does this area look like? Even if it's not perfect, it's okay. Here's my y equals to x squared, the line x equals to 1, the line x equals to 2, bounded by, right? In other words, it doesn't go above this thing, and it's in between this line, and of course the x-axis. So my function's x squared, so that's my radius, right? The radius goes from the axis of rotation to the curve. The curve is x squared, so that's what I'm plugging in there. So my area function is pi x to the 4th. So to find the volume, I pull out the pi and integrate from 1 to 2, x to the 4th dx. When I do that, I get x to the 5th over 5. Now I have to evaluate it between 1 and 2, and I go ahead and plug that in, right? 2 to the 5th is 32 fifths minus, right, upper bound minus lower bound. When I plug a 1 in, 1/5, so 32 fifths minus 1/5 is just 31 pi over 5 units cubed. Now I went into the book, and there's a couple of really good examples there. So like page 383, number 5, they actually have the picture there for you, much better than my picture. But anyway, you know, by now you should be very well seasoned in integration, U substitution, and all that stuff. So it's no wonder, you know, that you would have it here. So this is the picture that's in the book between 1 and 1 here. This is a y value of 1 right here, and this is the x value of 1, because this is the function. Okay. Again, if I rotate this thing, if I want to think of it sort of 3D-ish, I'm going to have this cone, and my radius, my circle, my radius goes from axis of rotation to the curve, and I'm going to have this circular disc. So again, it's pi r squared. That's what I have to integrate. Now, I can FOIL that out, right? If you can, if you want, it's fair game. You know, you could do this to get 1 minus 2x plus x squared dx and integrate it that way. Here I use substitution. I let u equal to 1 minus x, so the derivative is negative dx. So negative du is dx. And I went ahead and I pulled out my pi, replaced this with u squared, my negative du, and then of course I'm going to bring that negative out here. Then I went ahead and I changed the limits of integration. So when x is 0, u is 1. When x is 1, u is 0. What happens is this is backwards, right? So there's a little trick with integrals that I mentioned, and I don't know if you remember it or not, but when your limits are upside down, when the lower number is above and the smaller number, the bigger number is on the bottom, you need to flip that. And to do that, you flip it and you change the sign. So since this was already negative, a negative times a negative is going to make this a positive, and then I just flip it. Okay, and so now everything's in terms of u, so I don't have to back substitute. So I'm going to get u cubed over 3 from 0 to 1, and when I plug in I get pi over 3. Now let me just do this one over here the way it was, right? I'm going to have x minus x squared plus x cubed over 3 from 0 to 1. That's going to be pi times 1 minus 1 plus 1/3 minus, now if I plug in the 0 for all of those, I'm going to have a 0. Those are going to cancel, so I'm going to get pi over 3 cubic units. So I'm going to get the same exact answer. The problem is you're not always going to be able to expand them. Maybe some other weird function like the sine or something like that, and so you may be forced to use u substitution, but again, you should be well seasoned in that by now. So keep that in mind. There's another one, number 6, for you to try. The function's y equals to 4 minus x squared. Okay, so it looks like this, and again, this is in the book. This is number 6 in the book. The picture's there. Let me try and adjust this. It's a little blurry. So, you know, again, if I'm thinking about rotating this thing, I'm going to have this sort of sideways looking bowl thing. And if I slice perpendicular to the x-axis, I'm going to get circular discs. So that's the formula I'm using. My radius goes from the axis of rotation to the curve, which is just 4 minus x squared, so I'm plugging that in for r, and there's my integral from 0 to 2, right? 0 to 2. And, you know, again, I could maybe use substitution, but then I've got another x, so it's going to get messy. So rather than that, I went ahead and FOILed it out and integrated term by term. So when I integrate 16, I get 16x, I get 8/3 x cubed, I get x to the 5th over 5th. Now I got to evaluate that from 0 to 2 and not forget about my pi. So I went ahead and did that. Nice thing is since this bound is 0, when I plug the 0 in, that whole thing's going to collapse to 0. So now just a little bit of tedious fractional work here, cleaning up the fractions, and the final answer is 256 pi over 15 cubic units. That would be the volume of rotating this region of area about the x-axis from 0 to 2. And that would change depending on, you know, it would change depending on a lot of things. But for right now, what you need to know for the test anyway, like I said, you might have one question where you're going to have to use the disk method. And it's pretty simple to do because the formula is always going to be the same. The radius is always going to be whatever function's given. And that's it. Okay, so this was the disk method with a little bit of review on net and total distance traveled. And by the way, the area under the curve represents the total distance traveled. When you integrate the definite integral, that's an interpretation of it. You know, if I've got yogurt melting on the floor, or ice cream melting in a container, or anything like that, those are also, you know, if I want to find the total amount of yogurt that, you know, melted or dripped out of a container or whatever, those are all interpreted the same exact way, the definite integral from a to b of the function. So I'll try and find, you know, another rendition of one of these to show you. The next video is going to be about the washer method, which is a little bit different, but it's still pretty easy. Okay, so stay tuned.